net change or accumulation. Recall when we start with a function defining an amount, we would find the derivative to find the rate of change. Then, by learning how to undo differentiation with integration, we could start with a rate of change and integrate to find the amount at which the function has accumulated, or in other words, by how much the function has accumulated. So far, we have been thinking and working with integration as a representation of the area between a function and the x-axis, which is absolutely true. In addition to this purpose, integration can also be thought of as an accumulator, where it's summing up quantities over a given interval. In other words, as we integrate along an interval, we are accumulating an amount as we go farther and farther to the right. Let's consider the horizontal line defined by the function f of t is equal to 3, or this horizontal line. Let capital F of x be equal to the integral from 0 to x of lowercase f of t dt, and fill in the table below. Well, we can actually integrate this, so let's actually do so. If we're integrating from 0 to x of 3 with respect to dt, we would get 3t, and we would evaluate it from 0 to x, and if we substitute x in there, we get 3 times x minus 3 times 0, which is 0, so we just get that f of x is equal to 3 times x. So now let's use this to fill in the table. For 0, we would get a 0 here. If we substitute 1 in for x, we would get 3. If we substitute 2 in for x, we would get 6. Then we would get 9, 12, and 15, respectively. So again, here it shows all of the function values that we found for capital F of x. Notice, though, in the diagram that as x increases, you're accumulating more and more area. You go from 0 area to 3 square units of area to 6 square units of area. Then you would go to 9, then 12, then 15, then you'd go to 18, 21, etc. The fundamental theorem of calculus part 2 gives us the area on a set interval. And another way of thinking of this is the net amount of change on the closed interval from a to b. So the integral from a to b of f of t dt is equal to capital F of b minus capital F of a. Applying this to real-world physical situations, if x initial represents an initial time, then the function evaluated at the initial x value will represent that initial amount. In addition, if x is our ending value, then we can rewrite the fundamental theorem of calculus part 2 as it's shown here. The integral from x initial to x of f of t dt will be equal to capital F of x minus capital F of x initial. Rewriting the fundamental theorem of calculus as we did allows us to interpret its meaning as it would apply to a real-world situation. The definite integral is the accumulated change found by subtracting the initial amount from the total amount. So here's that last formula that we had broken down in terms of words. The accumulated change is equal to the total amount minus the initial amount. If we want to find the total amount, we can rearrange the equation accordingly. We have this integral from our initial x value to x of f of t dt being equal to capital F of x, or that total amount, minus our initial amount. If we were to add the initial amount to both sides, we would end up getting this equation where the total amount is equal to the initial amount plus the accumulated change. Suppose that C of t represents the daily cost or cost per day of heating your house during the winter, and it's measured in dollars per day, where t is time in days and t equals 0 corresponds to the first day of winter. Can we write an expression that represents the cost in dollars to heat your house during the first 60 days of winter? Let's try. The expression that we could create would be the definite integral, which would accumulate the cost for each day. So we would do the definite integral from 0 to 60 of our cost per day function with respect to, that's a function of t, and we can integrate it with respect to t with the dt at the end. And now that we can set up an expression for accumulation, let's try an example that actually finds the accumulation for the situation. Oil is poured into a tank at a rate of square root of the quantity x plus 2 gallons per minute. Calculate how much oil is in the tank after 7 minutes. Before we start solving this problem, it's important to recognize key words that are in the problem, such as rate. So the square root function is telling us a rate, and we have to determine how much, or the quantity that has accumulated of oil after 7 minutes have happened. So therefore, we need to integrate. So we're going to begin by setting up the integral, and it's our time, it says after 7 minutes. So the time period is going to be between 0 and 7 minutes. So those are going to be our lower and upper bounds for integration. So we have the integral from 0 to 7 of the square root of the quantity x plus 2 and then dx. Now, before we get started on integration, let's actually rewrite this to make it a little bit easier. It's going to be the integral from 0 to 7, but then instead of the square root of x plus 2, we could rewrite it as x plus 2 raised to the 1/2 power. Now this is a lot easier to integrate. And now, in order to integrate this, some of you may also elect to use substitution. I'm going to show those steps here, but it can also be done a little bit more directly. So if I use substitution, I'm going to let u equal x plus 2, or the expression that's in parentheses. And then du is going to be 1 times dx, or just dx. So then I would end up having the integral. I'm going to ignore the lower and upper bounds for now because I'm going to put the result back in terms of x before I evaluate. So we're going to integrate u to the 1/2 du. And then if we do integrate that, we'll have 2/3 times u to the 3/2 power. So then if we put that back in terms of x, that's going to be 2 times x plus 2 raised to the 3/2 power, all divided by 3. And we're going to evaluate that from 0 to 7. So we're going to substitute 7 in and 0 in, and then evaluate our expression. If we do 7, we'll have 7 plus 2 is 9. The square root of 9 is 3. 3 cubed is 27. So we have 2 times 27, which is 54, and 54 divided by 3 is 18. So we have 18 minus 0 plus 2 is 2. 2 raised to the 3/2, that's going to be a little bit more ugly. So we could do 18 minus 2 times 2 to the 3/2 divided by 3. And let's put that into a calculator. So we have 18 minus 2 times 2 raised to the 3/2 power divided by 3. And that's going to give us 16 and about 114 thousandths gallons. Let's try another example with accumulation. Oil is poured into a tank at a rate of the square root of the quantity x plus 2 gallons per minute. At time equals 0, there are 45 gallons of oil in the tank. calculate how much oil is in the tank after 7 minutes. Similar to before, the first step is to note the wording. It says that at t equals 0, there are 45 gallons of oil in the tank already. So that means we're going to have to use this initial amount given to us to determine the rest of our integral or the full equation. So it has to do with the f of x being equal to f of the initial x value plus the integral from the initial x value to the ending x value of lowercase f of t dt. Remember, the total amount is equal to that initial amount plus that accumulated change. So we have that capital F of x is equal to the function value at the initial amount plus the integral from our initial x value to x of f of t dt. Well, we have this initial x value, or the initial value when time is 0. It's 45. So we have 45 plus the integral from a, or time is equal to 0, up to 7. That's going to be our b value, or our upper bound. So our function, or the integral, is going to look just like this. 45 plus the integral from 0 to 7 of the square root of the quantity x plus 2 dx. Next, what we can do is we can rewrite our integrand without the square root. Instead, we could write it as a rational exponent. So we'll still have 45 plus the integral from 0 to 7 of x plus 2 raised to the 1/2 power dx. Now, since we have a polynomial raised to some sort of power, let's use u substitution to help us with this integration. We can let u equal x plus 2, and if we do that, then du is going to equal dx. So now we're going to have 45 plus the integral. I'm going to ignore rewriting the lower and upper bounds in terms of u, because I'm going to use the x values, like I'm going to substitute x back in. So we'll have u to the 1/2 du, and if we do integrate that, we're still going to have the 45 out in front, plus we'll have 2/3 u to the 3/2. And now let's substitute u back in to be x plus 2. So we'll have 45 plus 2 times x plus 2 raised to the 3/2 power, all divided by 3. And we're going to evaluate this from 0 to 7. And when we substitute our x values in, first 7 in for x, and then 0 in for x, we can then evaluate it. Well, 7 plus 2 is 9, square root of 9 is 3, and 3 cubed is 27. So we have 2 times 27, which is 54, divided by 3, that's 18. And then we're doing subtract 2 times 2 to the 3/2 power, all divided by 3. And then we're going to add 45 to this. So we can see actually at the top of our calculator, we did the 18 minus 2 times 2 to the 3/2, all divided by 3. And we ended up getting 16 and 114 thousandths. And then if we add 45 to that, as this problem is having us do, we get 61 and 114 thousandths gallons as our final answer here. For time values between 0 and 31, including both endpoints, the rate of change of the number of mosquitoes on a tropical island at time t days is modeled by r of t, which is equal to 5 times the square root of t times the cosine of t divided by 5, mosquitoes per day. There are 1,000 mosquitoes on tropical island at time t equals 0. According to the model, how many mosquitoes will be on the island at time t equals 31? Let's try to find out. In this case, we need the final amount found by adding the initial amount, which is 1,000 mosquitoes, to an accumulated amount, which we're going to find using the integral. So we're going to have the initial amount plus the integral from 0 to 31 of r of t dt. The next step is to fill in the information that we know. R of 0 is 1,000, and then we can fill in this function in for r of t. If we do that, here's what we have. We have 1,000 plus the integral from 0 to 31 of 5 times the square root of t times the cosine of t divided by 5 dt. And the next step is going to end up being to integrate with a calculator. Reason being, this is not an easy use substitution and integrate. So let's actually use the graphing calculator to our benefit here. So we have integrate, it's found in the math options. It says nderiv and then fn int. That fn int means function integration. So if I select option 9, I can fill everything in. So we're going from 0 to 31, and we're doing 5 times the square root. You can elect to use x as long as you put dx here, or you can put it in terms of t as this question does. For ease, I'm going to put it in terms of x. So 5 times the square root of x, and then I'm still in the integrand because I want to add more to it, the cosine of x divided by 5, and then close the parenthesis for that angle. And now the integrand is complete, and we have to put dx here because I am integrating with respect to x. So when I do that, it gives me an output value of negative 35 and about 665 thousandths. And then if we add it, you can either elect to round that up or keep it the way that it is. And when you do the subtraction and do 1,000 plus that answer that we just found, we get 964 and 335 thousandths mosquitoes. Or if you were to round it to the nearest whole number because you have mosquitoes, that would be roughly 964 mosquitoes.